Hello, everybody. Let's take a look at what remains of section 3 that we started discussing in class here. So, get myself a new slide. And so, the big idea with how this works is to recap. So you have exponential form, which is probably what you're more accustomed to. Y is equal to x to the n power. That is kind of the way you would write something with an exponent that you're probably more accustomed to. And to maybe give you an idea of what that might look like, for instance, 9 is equal to 3 squared. That would be an example of an exponential statement. So on the flip side, if you were to write this as a logarithm, you would write it as log of base x. So x is the base because that is the big thing that is holding up the exponent. So this is log of base x. You would put the result that you would get from evaluating the exponent. That, in this case, I called it y. And then what the log equals is n. The log is equal to the power. If we wrote this statement, 9 equals 3 squared, as a logarithm, what that would look like would be log base 3. You would put a 9 inside it, and what that would equal would be 2. That's how logarithms work. So if we pick up where we left off with part D, we're rewriting these in exponential form. So we have log base 9 of 3 is equal to n. The way you would write that with an exponent is you would write that as 9 raised to the n power, because the 9 is the base. That's the little number down below, which syncs up with the number down below that's holding up the power. The log equals the power, which in this case is n, and then what that works out to be would be 3. So 9 to the n power happens to be 3. For part E, log of base 6 of 1. If we set that equal to just n, whatever the power would be that we would need, the way you would write that is you would have 6, you would raise it to the n power, and then that would equal 1. Finally, for part F, we have log base 5 of 5, and that is equal to n. Again, just an arbitrary value of something to be just a placeholder for the exponent. The base is 5, 5 to the n power. That is equivalent to 5, because that is the thing inside. They also tell us to solve them. So, fun fact, a 1/2 power is the same as the square root. So if you did 9 to the 1/2 power, that's another way of saying the square root of 9. The square root of 9 happens to be 3. So in this case, n would have to be 1/2 for that example right there. For this next one, 6 to the n power turns into 1. You've probably encountered the fact that in order to turn a number into 1 with a power is you would need the 0 power. This would mean n equals 0. For this one, if you have the exact same number, 5 to the n equals 5, that means n is equal to 1. because when the power is 1, it doesn't really do anything or change much of anything. So that would be what the value of n equals in that situation there. Here we are given exponential equations, and then we are asked to change them into log notation. So if we look at this first one here, 16 is equal to 2 to the x power. Now, the thing to notice is that the base of the power is a 2. So if we wrote it as a logarithm, that would mean we would need the log of base 2. What the logarithm equals is what you put inside the logarithm, inside the parentheses. So this would be log base 2 of 16. And then what logarithms do, logarithms are equal to a power. So a log equals a power. Whatever the log equals, it is the power. So in this case, the power is an x. That would mean log base 2 of 16 would equal x. That is how you would rewrite that in log notation instead of the exponential notation that you're probably more accustomed to using. For part B, we have 0.001 that is equal to 10 to the negative 3. If we were to rewrite that, you would write that as log of base 10, because the base of the power is 10. What you put inside the logarithm is what the power equals. So in this case, 0.001. And the log equals the power. If the power is negative 3, that means the log should equal negative 3. Now, this one's kind of a special one because there is something known as the common log. And what the common log is if you have log of base 10 of, let's say, z, that is actually equivalent to just saying log of z. So if you see just the word log and they don't specify what the base is, that means the base is understood to be 10. The number system we use is a base 10 system, and so the common log is log of base 10. So the way that you would write this is you would just say log 0.001 equals negative 3. And if you don't write the base, that just means that it's understood that the base is a 2. If we go to a calculator real quick here, so if you use like a graphing calculator or a scientific calculator, many calculators have a log button on them. And so if you were to type log, and then it actually changes it because it recognizes that. And if you do log of 0.001, as promised, that gives you negative 3. The reason for that is because if you do 10 and raise it to the negative third power, that's 0.01. The reason that works, by the way, if we change this to a fraction, 10 to the third is 1,000. And what the negative does is it tells you to do the reciprocal of that. So that means it's 1 over 1,000, which in decimal form is 0.001. But that is what that means. That's how that works the way it does. If we go to the function menu, the log button for this one is over here in the function menu. And lots of handheld calculators also have log buttons on them. Part C, we have 70 equals e to the t. Now, e, which we introduced in the previous section during class, e is just a number. There's nothing that mystical or like special about it. It's a number. It's kind of like pi. It's this kind of wackadoodle decimal, but it's, you know, it's a number. That's all it is. So if you wanted to do a log and the base was e, what you would do is you would do log of base e. You would put 70 inside of there because whatever it equals as the power, that's what goes into the logarithm. And then whatever the power that is, that's what the log is equal to. Now, again, kind of like 10, e is another special number. It's a special logarithm. It's a special base. This one is called the natural log. You make me feel like a natural log. Anyway, I don't know why I did that. But anyway, if you have log of base e of z, the way that that's often written, instead of log base e, usually you will see that written as ln of whatever's in there. In this case, I said z. So ln is short for the natural log. Now, for those of you sticklers out there, you might be like, why is it ln rather than nl for the natural log? The reason is the dude who came up with this, Leonhard Euler, who was Swiss, he spoke French. And fun fact, in French, you would not say the natural log, you would say the log naturel. And so the adjectives come after the nouns in French, just like they do in Spanish. And so anyway, that's why it's ln. And plus it's consistent because like log and ln both start with L. But I'm not the one who made this stuff up, but that's what it is. It's ln. And so this would be, the way you would write this is you would write it as ln of 70, and then that would equal t. And then fun fact, if again, you got yourself your favorite scientific calculator or graphing calculator, you might notice that it will have an ln button on it. Here's where it is for this one. You can do ln. We can actually figure out what ln of 70 would be. That happens to be 4.2485. But lots of calculators worth their salt are going to have an ln button on them. And fun fact, if you did ln and e together, it would give you 1 because e to the first power would equal e. So that's what log of base e would be. But anyway, there is that one there. That would be the natural log, or ln. All right, what else do we have going on here? Convert to exponential form. All right, so they give us log statements, and our goal is to change them over into exponential statements. Okay, so for part A, if I have log base 2 of 32, and that is equal to 5, the log equals the exponent. The little number down below becomes the big number down below. This is a 2 down below. That's going to be a 2 down below. The log equals a power. That's going to be a 5. This is going to be 32. 2 to the 5th equals 32. For part B, log base A of Q is equal to 8. The base, the number down below, is the same as the big number down below. That's going to be an A. So we're going to have A as our base. The power is going to be what the log equals. So in this case, that's going to be 8, A to the 8th power. And that is going to equal capital Q, apparently. There you go. A to the 8th power, would equal big Q. Right on. Let's see here. Log base T of M is equal to X. So the number down below is the number down below. That's the base. That's going to be T in this case. We'll start with T. We're going to raise that to what the log equals. That's the X power, T to the X power. Whatever's inside the logarithm is what you would get from working out the power. So in this case, that's capital M. T to the X power is going to equal capital M. Okay, so far so good. What else do we have in store for us? Evaluate using a calculator. All right, these should be some of the simplest problems ever. The main thing is make sure that whatever calculator it is that you're using, make sure you know how to find the log button on the particular calculator that you're using. Now, some calculators you have to type in the number first and then hit the log button. This one that I have here in my hand actually works that way. If I wanted to work out 645,778, do the log of that, I would have to type in 645,778. So I would have to type that in, and then up at the top of this one is the log button. And if I push the log button, it'll evaluate the log for me. Other calculators, you just kind of type them in the way it's written. So if it is, what is it? It's 645,778. So if I do log 645,778, and if you do that, that's almost exactly 5.81. So that is that's what that one's going to be equivalent to. So again, the main thing is just make sure you know how to use the specific piece of technology that you have in front of you and that you will be using on your exam when we go over this stuff. But however you're going to do it, just make sure that you know how to do it. There's really no reason why anyone should get questions like this wrong. Okay, for the next one, I did ln of that decimal, which is going to be a negative number. And so if we do ln, and hit the ln button, and what is this? Zero, it's a 0 point. We got 4 zeros and a 239. 0.1234, 239. That is negative 10.64. So that's what that will be equivalent to for this one. So negative 10.64. If you try to do negative 3, it's going to give you an error message. So if I try to do log of negative 3, I did it on this calculator and it says error. So fun fact, that is undefined. And so the idea with this is you can't evaluate logs of negative numbers. And actually, hang on a second. I might have, hold on. I think I did log, I was supposed to do log of that. I think I actually did ln of that now that I think about it. Yeah, okay. It's supposed to be log because they're all logs. Was that 0.00000239? That's supposed to be negative 4.62. There's another one where we do natural logs. Negative 4.62. There's that one. Let's see. This one we're doing ln. So that one we actually worked out. The second one, what is that? That was negative 10.64. This is negative 10.64. That's part B. What is ln of 645,778? 645,778. That is 13.38 is what that is. Fun fact, part C is going to be undefined. Because just like before, if you try to take the logarithm of a negative number, that is not going to work. So that will be undefined. ln of e, I think we actually maybe did that earlier. It's actually equal to 1. If you do a log of the number itself, it's just going to spit out the number 1. So log base 10 of 10 would be 1. Log base 8 of 8 would be 1. That's true of anything. And then if you do a log of 1, or ln of 1, that is going to be 0. Because the question this is answering, what power do you need to turn it into the number inside? And if you're going to do a logarithm and your goal is to get 1, the power would be using the 0 power to turn that base into 1. So any log of 1 is going to equal 0 every single time. All right, so that is that one. So again, just make sure you know how to use the calculator that you have at your disposal. All right, we're going to talk about a log property that lets us evaluate any log of any base. You might be thinking to yourself, we've seen this dude do logs of other bases like log base 5 or log base 8 or log base 2. Like, what's up with these calculator people being so lazy that they can't like let me do logs of other bases? Like, why do they only have log base 10 and log base e? Like, what gives? What's up with that? Well, the reason why calculator manufacturers can get away with doing that is because of a little something known as change of base. This is not to be confused with Ace of Base, the Swedish girl group from the 90s that gave us such hits as It's a Beautiful Life and I Saw the Sun. Please do not confuse this with Ace of Base. This is change of base. And so change of base is this formula right here. So if I want to do log base B of, let's do log base B of C, then it turns out that is equivalent to doing log C divided by log B. Or another way you could do it, log base B of the number C is equivalent to ln of C divided by ln of B. So be sure to use parentheses when dividing logs. The most common mistake when doing this kind of thing is students sometimes neglect to close the parentheses when they're typing this in, and it can sometimes mess you up. So if I were to do log of, what is this? Let me write it down first. So if I'm going to do, they say do it once with common logs, then do it again with natural logs. So if we're going to do log base 5 of 8, that would be equivalent to doing log of 8 divided by log of 5. And the way I always remember this is, you notice the 5 is the one that's down below, so the 5 is the one that's down below. So you do the log of the inside divided by the log of the base, the log of the number down below. So if we were to evaluate this, we're going to do log of 8 divided by log of 5. So let's get ourselves a calculator and figure out what that is. So we're going to do log of 8. I'm going to close the parentheses and then divide it by log of 5. And if I do that, I get 1.292. So the correct answer is 1.292. It will not matter if we use common logs or natural logs. You could also do it with any pair of bases you felt like. So you could, if you wanted to, do ln of 8 and divide it by ln of 5. And if we do that, we should get the exact same thing. ln of 8, let's do the parentheses, ln of 8, divide that, and then do ln of 5. And that, again, is 1.292. If you don't put the parentheses there, you might end up messing yourself up. If you do ln 8 divided by, this calculator is actually smart enough. But like if you did something like this, ln of 8, and then you don't close the parentheses and do divide, you sometimes run the risk of doing that if you don't close off the parentheses, and it can go haywire and mess you up. It's usually good, just to be safe, to put exactly what you want in the parentheses so that it is clear what belongs in the log that you're doing and what does not belong in the log that you're trying to work out. So that is how change of base works. Okay, next we are asked to provide graphs of log base 5 of x and also ln of x. I'll tell you what, let's do these on 2 separate slides here. Now, if I'm going to graph log base 5 of x, the way I would need to do that is I would need to do y equals, and I'm going to do log of x and divide it by log of 5. I'm going to use change of base, and that will let me make a graph to use a base of a log that's not one of the standard ones that comes automatically with my calculator. So let's go to, let's get the graphing calculator pulled up here. So we're going to do y equals, we're going to do, what was it? Log x divided by log 5. So we're going to do log x, we're going to put that in parentheses, the x, we're going to divide it by log of 5. And then when we do that, we get that very lovely graph right there. So that is kind of how most sort of garden variety, that's how most kind of garden variety, that is so not what I wanted to do. Copy image. Ta-da! Okay, there you go. So that is kind of the general shape of a log equation. It's kind of flat along the y-axis here, negative land. It gradually curves and starts bending over this way. It takes its dear sweet time, gradually working its way up. One thing I want to say about this graph before we move on, because it's log base 5, we would need to have the number 25 to get to the number 2. So if we zoom out here, because 5 squared gives you 25, this graph at 1, it's going to equal 5, because 5 to the first would equal 5. And you'd have to go all the way to 25 to reach 2. And that's because 5 squared is what gives you 25. That's what these logarithms are telling you. They're saying, what power of 5 do I need to turn a 5 into a 25? And the answer would be a 2. And it'll take its dear sweet time working its way over to 3. Fun fact, 5 to the third power is 125. And if we go over here, as I said, this graph takes its dear sweet time getting up to 3. You have to go all the way over to 125 to make it to 3. Because again, this graph is very, very slowly working its way up. So there you go. Here they ask us to graph ln of x, so we can do that without a whole lot of trouble. Let's go back to kind of more of a standard looking window here. So there you go. That's what ln of x looks like. Let's copy this image. Ta-da! There you go. Shouldn't be too hard for us. Graph these and describe the shifts. Okay. We've talked about this kind of stuff before. What's going on here? If you're changing something with the x, it affects the x direction. So this one, if it's +3, that's going to send you left 3, is what that's going to do. For part B, I'm going to write this as -1/2 ln of x. And then I'm going to put +3 on the end. What this is going to do, the negative will flip vertically. The 1/2, it's going to make it 1/2 as tall. When you change something with the y, it does changes to the y direction. So that'll be taller or shorter. And the nice thing about changing y is that what you see is what you get. Meaning that if it's a half, your intuition might be that it gets half as tall, and that is indeed what happens. It doesn't do kind of weird backward stuff. The +3, what this is going to do, this is going to move you up 3, is what that will do to your graph. This one here, when you have a -1 on the inside, what that will do is it will move the graph right 1 spot. And then this one's kind of an oddball, but what the absolute value does, it's going to vertically flip only the left side, that is negative. That's what the absolute value is going to do, because absolute values only take negative numbers and flip them up to turn them into positive. So it's not quite the same as just flipping the entire graph. It only takes the negative half of the graph below the x-axis and flips that part of it up above the x-axis. We will finish by doing a word problem here. So let's start with parts A and B. So they say the formula for walking speed in feet per second with a city of P population in thousands is given by this formula. So W of P equals 0.37 ln of P plus 0.05. Find the average walking speed of Billings, Montana, population 106,954. So because it's in thousands, what we need to do is we need to take the population and divide it by 1,000. Because when it says in thousands, we're not actually going to use the number that we're quoted directly. We're going to divide it by 1,000. So in this case, Billings, Montana has 106.694. We're going to put that number into the formula that they give us. So W of 106.694, or 954, rather. So W of that number is equal to 0.37 ln of 106.954 plus 0.05. And if we get ourselves a calculator, we can work out what that is. Let's see what we have here. What do we got? We have 0.37 ln parentheses 106.954. Close the parentheses, add 0.05, and when you do, you get 1.78, and that is feet per second. Cool. So that's the very leisurely moseying pace of people who live in Montana. Now, Chicago, those are big city folk. They are booking it. They got places to be, things to do. We're going to take the population of the city of Chicago, which is like 2.7 million. We're going to take it, we're going to divide it by 1,000, which is going to be 2714.856. Because again, that means we're going to, when it says in thousands, we have to divide the population by 1,000. And we're going to put this number into this function that they gave us. And we will see what the average walking speed of people who live in Chicago is. 0.37 ln of 2714.856. I'm going to add to that 0.05, and we can see what that will be. Get our trusty calculator here. 0.37 ln parentheses 2714.856. Close the parentheses, add 0.05, and when you do, you get 2.975. If you round it off, it's 2.98 feet per second. So again, those big city folks in the city of Chicago, they got places to be and things to do. No idle moseying around these parts. We'll move this thing over here. Maybe that way it won't block you all's view of what I've got going on here. Then let's see what we have for the last two parts of this. Graph the function and then estimate the population of a city with that walking speed. Okay, so let's get our graphing calculator out here. What do we got? We got 0.37 ln of x, and we're going to add 0.05 to that. And then let's start with that. All right, so that's going to give us a graph. There we go. There's the graph. Let's get this graph. Copy image. We'll put it right there. Ta-da! There you go. That's part C. That's what the graph looks like. Estimate a city's population with a walking speed of 2 feet per second. Okay. So we know the ones we already did. It's got to be bigger than the population of Billings, which was like 1.78, but it's got to be smaller than the population of Chicago, probably smaller by quite a bit. So I'm going to make a ballpark guess that it's probably somewhere around, I don't know, 150, 200,000, somewhere in there. That's just kind of a rough guess. What we can do is graph y equals 2. So that's our target. That's what we're trying to meet. Let's see if, let's have x go up to, now Billings was 106. Maybe we'll go out to 200, which is like 200,000 maybe. Oh, I think it found the intersection point. So there you go. The intersection point happens at 194.46851. So from graph, it meets y equals 2 at 194 point, what is that? 194.46851. 46851. Now, that's the population in thousands. Again, this is the population in thousands. So we're going to take 194.46851 and multiply it by 1,000, which will give you 194,468.51. And if we round that off, that's about 194,469 people. That would be the answer to the question. It's very precise. Somewhere around 194, 195,000 people, somewhere in there. All right, and with that, we are finished with section 5.3.